Hello everyone, I'm Hamandi and I will be presenting our work on direct acceleration feedback control of quadrotor aerial vehicles. During this presentation, I will first introduce our direct acceleration controller and show why we need the body acceleration filter, which I will then explain. After that, I will show the controller performance in a quick experimental campaign, and finally, I will conclude the presentation. In this slide, we show a classical quadrotor controller, where the position feedback loop finds the desired acceleration to reach the desired position and velocity. Desired thrust and platform direction are then calculated from the desired acceleration based on the nominal model. Finally, propeller speeds are calculated to achieve the desired thrust and direction. The problem with this controller is when the mass or lift change from the nominal values, or if the platform is subjected to external disturbances. In this case, the nominal model is no longer valid. As such, we suggest to remove completely the model inversion and close the loop on the platform acceleration control. So, to zoom a bit more on the acceleration controller, we can see from this graph that the model inversion requires the knowledge of the platform mass, gravity direction, and external forces, which is usually unknown but rather estimated. Instead, our controller shown here calculates the desired force as the feet forward of the desired acceleration, in addition to an integral of the error between the measured and desired acceleration. Alpha here is an estimate of the platform model. However, we show that the controller is stable for any alpha and beta positive, even if the estimate is not accurate. For these alpha and beta, the controller is shown to asymptotically drive the platform acceleration to the desired one without requiring an estimate of external disturbances, platform mass, and it is robust to changes in aerodynamic properties and parameters. Our controller can be reformulated as a PID controller. However, the difference between the direct acceleration controller and the PID is in their inputs, where the direct acceleration controller uses acceleration measurements in addition to position and velocity, where the acceleration measurement is usually a high frequency measurement as opposed to the position and velocity measurements. We showed in our paper that since the controller uses high frequency measurements in addition to the low frequency measurements, we can increase the controller gains without losing stability, while the PID cannot do so. On the other hand, the position and velocity measurements naturally damp the noise in the acceleration, while the direct acceleration controller requires the use of the IMU measurements directly, even with their noise. As such, we had to introduce a new IMU filter for this task. We observed that IMU measurements always have noise at the frequency corresponding to the propeller rotational speeds along with their harmonics. As such, the IMU measurement is a combination of low frequency body acceleration in addition to high frequency sinusoids at the propeller rotational speeds. Classically, a filter such as a low-pass filter is employed to remove these oscillations. However, a low-pass filter has a few drawbacks. First of all, a low-pass filter is a linear filter, where it multiplies the signal at each frequency by frequency-specific value. As such, if the noise has a large amplitude, as shown here, it can still be present in the filtered output. Of course, this can be overcome by reducing the cutoff frequency. However, the low-pass filter also delays the signal, and this delay becomes more significant when we lower the cutoff frequency. As such, we present a regression-based filter, shown here, where we model the platform acceleration as a p-order polynomial, and we model the noise from the propellers as a sum of cosines and sines at the propeller rotational speeds, along with their harmonics. Then we fit this model to the last n IMU measurements, and as such we find the amplitude of the noise as well as the model of the platform acceleration. As such, this filter removes completely the noise irrespective of their amplitude while adding no delay to the filtered signal. This filter is easy to implement and runs in real time on a quadrotor vehicle. In the following slides, we try to assess the controller performance in real-world scenario experiments. In this first experiment, we ask the platform to approach and pick up an object of unknown mass. This experiment shows that despite the change in mass, the controller flies the platform normally, since it does not require an accurate knowledge of its weight. In this second experiment, we show the platform flying below a larger platform, generating a turbulent flow. This experiment shows that the controller can fly the quadrotor stably in a turbulent flow. In this third experiment, we show the platform flying at high speed in a lemniscate shape at 2.8 meters per second. This experiment shows the stability of the controller following agile maneuvers. Finally, in this final experiment, we compare the controller's performance against a PIDs when subjected to a step response. The step response was generated in code to assure the repeatability of the experiment. We can see from this plot that for both controllers, the platform rejects the disturbance faster as beta increases. However, we can see that for the PID, at beta equal to 4, the controller stops being stable. On the other hand, the direct acceleration controller is stable for beta up to 12. As such, the direct acceleration controller can be made more robust to external disturbances than the PID. To summarize the paper, we introduced a direct acceleration feedback controller. The controller can fly a quadrotor robustly without an accurate knowledge of the platform mass or aerodynamic properties. We also introduced a zero-phase, real-time IMU filter that extracts noise caused by the propeller vibrations. Finally, we assessed the proposed controller and IMU filter in a campaign of real-world experiments. At the end, we would like to thank our sponsors for their support financing this paper, and I would like to thank everyone for watching this presentation.